I'm Dan Slep, and the CEO and the founder of ChemCubed, or Chem3 LLC. I was asked to present what we do as a company. I'll tell you a little bit about myself first. I have been working in the digital printing industry for over 30 years. I ran another company prior to starting ChemCubed, and my customers were 3M, Xerox, HP, Armstrong, a bunch of Fortune 500 companies, and other medium-sized companies as well. I was on a lot of engineering teams in terms of building printers. The printers we worked with back in the graphics were about 10 feet wide. They did building wraps and trucks and so forth. Well, that industry got a little bit old, and everybody knew what electrostatic printing was and inkjet printing at that time. But additive manufacturing became a big deal. So additive manufacturing, noticed 3D printing on a small scale, but in industrial levels, additive manufacturing was starting to hit. But one thing that was missing in additive manufacturing, or what there was a great need for, was materials. Inkjet printing, all sorts of printing, screen printing, all of that's been around for many years. But where do you get the materials to build these items in additive? So about 9 years ago, coming up to 10 years ago, started ChemCubed. We had a space here at the Energy Center. By the way, my bachelor's degree is in physics. Studied chemistry and got my PhD in materials here at Stony Brook. So I had a wide cross-disciplinary team working with me. I had learned a lot, or a little bit, about everything and not enough of anything, actually. But I was able to start the company, and what we did back then, when we first started, was we sat around and tried to figure out where our targets were. What are we going to do first? What materials are we going to make? We know additive is big. We've got a couple of big companies beginning to address additive, inverted 3D systems, and Stratasys, and MakerBot. But what are we going to do at that time? I ended up getting a project with Northrop Grumman. And they wanted us to develop inks in a whole system of printing antennas, different antenna designs. Found out that it was stealth antennas. So they wanted to experiment with different antenna designs, and they needed a printing system to go ahead and do this. So we went ahead and started trying to figure out how we're going to do this. We entered with an engineering company to build a printer for us. It's 4 foot by 4 foot printer. It was an inkjet printer. Why we went to inkjet so we could do multiple different materials and build these antennas. In terms of materials, that's where we excelled. Obviously, that was our business. And we developed our flagship circuit material, a silver ink that actually has no particles. And I will talk about that a little bit as we talk more about what we're doing in electronics. So we started as a research and development company. We were housed at the Energy Center between my partners and I at the time. We had many years of experience between marketing and understanding the market of printing, and mostly in the graphics area. Now we're going to get into the area of additive electronics. Due to the Northrop Grumman, we developed an additive electronics mechanism. Well, Northrop Grumman went ahead and discontinued the program internally because people shifted around. I mean, we ended up with this printer as people or other companies started asking us, what can we do in electronics? And we started showing what we had available, and then we excelled. So right now, these are all the key market segments ChemCubed is in. And there's a lot of overlap between aerospace and electronics, advanced manufacturing, automotive, all sorts of things. But we've got our fingers into all of these plus. We're into dental, we're into medical. We have materials going through the FDA right now. But back toward electronics, we ended up in 2 divisions. We have what we call our NanoCube division. that's where we develop materials for specific applications, like for the biomed companies that need materials for FDA and so forth, optical materials and things like that. The electrojet brand materials is probably more of what you're all interested in. That is our low-hanging fruit and our main source of income revenue. As I said, we built a printer, we developed inks for it, and I'm going to go ahead and define what that means, what the multi-layer, multi-digital printing solutions in electronics actually means. So what is printed electronics? It means we're additively printing the circuit. We'll talk about traditionally how it's made, but right now we'll take a substrate like FR4 board, Rogers board, Kapton, even polyester. Print on materials, and we print our circuits. We print a dielectric between them. We'll print other circuitry. We'll leave vias between them, and we'll make a multi-layer board. Why is that so interesting? Well, this is just from a few years ago. This is how big that market is growing. It's growing exponentially. There are more and more people involved in designing around it. How many of you are interested in design aspects of electronics and circuit boards and PCBs? So this is what you're going to end up doing, as opposed to the traditional methods that they're doing them now. And what's driving this is actually people like Boeing, Lockheed Martin. I'm just mentioning my customers: Toyota, Molex, huge companies that are designing around additive rather than designing in a subtractive manner. So right now, the different types of printed electronics, or different types of printing systems, are all of these. The red ones are actually very digital. There's direct write, there's thermal transfer, there's actually emerging technologies where they're printing 100% metal, they're molten metal. There's a technology which is really interesting called aerosol jet, and that takes ink and aerosol jets and it can print lines down 10 microns. So with microelectronics and everything trying to get smaller and smaller, that's a really cool technology. Not only that, it can print on 3D objects. So you can take an object like this, and it uses something like a 5-axis CNC machine, and we'll be able to print circuitry right on top of an object. What are our goals here? Well, imagine a drone, and you have a lot of ribbons and a lot of electronics. Imagine it all being printed all at one time, an arm of a drone or something of that nature. One of my partners actually was hoping before he exited the company that someday we will print a whole airplane. I was telling him it's kind of foolish at this point, but that was his desire. We stood with aerosol jet and inkjet, mostly inkjet. The reason inkjet is why we stuck with inkjet is because it's got multi-channels. You can put different materials. So a regular 3D printer, how many of you have 3D printers at home or worked on 3D printers here? They all print with generally just one material at a time. So you can make a Lego toy. You can make all sorts of valves, mechanical items. You could but adding multiple materials, some of these bigger additive machines could do that. You now have a variety of things you could do all at once as you build. So we knew that inkjet was going to be the way that we're going to be able to do additive manufacturing of electronics. And so that's where we headed and strove to go into inkjet. So the benefits of printed electronics over traditional methods: fewer materials, less energy. The design and development aspects are faster. You can have an additive manufacturing electronics printer sitting on your desk while you're at work. Make a prototype design, which would normally take, if you take a design, send it out, have it done 4 to 6 weeks. You can get it faster if you pay a lot more money for it. It costs thousands of dollars to do. Instead, you have a printer sitting on your desk and develops, and you can check out your design right away. So while we were at the energy center, there was another company right next to us that was converting UPS trucks to EV. You're probably familiar with the company. But they once asked us, can we print a circuit for them? They needed it real quick, and we went ahead and did that. And we placed the components on it, gave them the circuit, the PCB board right away within 24 hours. The next morning, they came to us and said, well, we kind of messed up on our design. Can you reprint it? We had 10 boards for them right away. We messed up on the design. Sure, give us the next design. We printed that for them. Within, that same day, they had the 10 more boards that were functional at that point. That took 2 days. That would have been months and months and large expenses on their part that we were able to do in just a couple of days and help them out. That was a good proof of concept for us of what we're capable of doing. So, and that was about 8 years ago, 7, 8 years ago. We've expanded quite a bit. So what I'm saying is a lot of parts of the design aspects, the designers in engineering are, so I'm talking to engineers from Boeing, from Lockheed, and they are re-engineering or redoing the designs in a manner that could be additively printed as opposed to traditionally developed circuit boards. Why is it so sustainable? So let's look at the two different methods, additive versus giant. Traditionally, the way a circuit board is made, if you send it out to a company and you want hundreds of boards made, what they would do is take a laminate FR4 board, regular PCB board, copper plated, and they'd give you the design. And it could be a multi-layer design. Then they have to etch away the copper where they don't want copper. For every square meter of circuit board that they etch away, they contaminate 4,000 gallons of water. That's significant. What do they have to do with that water? Well, they have to scrub it, clean it up, get the copper back so they can reuse it. And that's a lot of hands-on. Not only that, that's only one single board. They have multi-layer boards. Now they have to laminate, a lot of hands-on work. So that's why it's taking weeks for a regular board to be made. In our method, where we're printing, we'll start with an FR4 board on the bottom, and then we just print silver, dielectric, silver, dielectric. And go ahead and print the inkjet board. So I'll just take a step back. How did we get there from that original Grumman project? Well, when they concluded the project, I had other people come to us and say, "What can you do in electronics?" Well, we built this printer before, so we can rebuild it. Then we sold one. Then we sold another. Then we sold a third. Talked to the engineering company whether they'll be able to sustain it. They gave us exclusivity, and now we have about 40 to 50 printers out there, which is pretty good. But we're only beginning to get steam after that. COVID obviously hit us pretty hard, right? We got to shut down. All the engineers at all the companies are working from home. None of them are in the office. None of them could test PCBs. None of them could do anything. So we did the best we could through COVID. I actually had 2 partners at that point. They've sold their other companies previously and were ready to retire. So I bought the rest of the company from them. They didn't think we were going to make it, but we excelled after COVID. It was good for me, not too great for them. Saved us millions of dollars, and we're able to excel past that. So now we do have these printers and these technologies that we can go ahead and share. Okay, I should have turned the music off, but that was a picture of the printer itself. Here's the front end with the software. What you have is a design, say that's the bottom layer, and this just shows how it's almost like a graphics printer. So it's got front end software. You assign a color to it at whatever resolution you want. So you can do grayscales, you can do as much ink as you want to put out down on the printer. And then you just kind of send that first layer to the printer. What we've done with the printer, on the log for a while, is that we've actually put optical alignment systems on it. That's a heated vacuum plate where that ink actually sinters. And within 5 minutes, it's a clear ink. It's got no silver particles. And when it's sintered, it's 100% silver. That's just the chemistry of it. That's our alignment system. We can actually line things up to 3 microns. So we can create, so we know where we are in the vias. And we can actually plate the vias from top layer to bottom layer where we leave holes in the dielectric between layers. So now this is a sample of 2 conductive layers. The bottom conductive layer you saw printed first. We've got amber color is a dielectric that's in between, and then the connectors on top is the second conductive layer, just as an example of how that all works. Now, this whole thing was printed within 20 minutes on some cheap PET. Because we sit at such low temperatures, the dielectric is a UV cured dielectric. This is a sample of it on FR4 board. This is a sample of it on Kapton, and this is a double-sided board. This is the other half of the double-sided board. The double-sided board is interesting. You can take a pre-drilled board, print on one side, as many layers as you need to print, align it, turn it over, and you can actually plate the vias with the silver ink at the same time to make the top to bottom connections. This particular board was designed in some John Hopkins experiment or whatever, but they allow us to use it to show. But we don't need that again. So this company, it's not actually a company, it's an institute in San Jose called Netflix. When we were doing all of this design work, we didn't know there were other people actually doing this stuff too, or close to it. So there's a whole infrastructure industry. So Netflix is actually government sponsored. It's a government institute. Most of its money comes from the AFRL, so the Air Force research labs. Also, we work with the Army research labs. We work a lot with the DoD. But we installed the printer on their request, wanted it to their lab. They've got a huge facility with all sorts of SMT equipment and drilling equipment and electronics equipment and electronics printing. And Netflix really is interested in flexible electronics. We saw that we were printing on Kapton and on PET. The thing is that our ink is also has 17% elongation, so you can bend it, just not freeze it, but you can bend it to a 1 millimeter radius. So you can imagine a circuit board that you can bend 1 millimeter radius. So Netflix got our printer. They had still projects they had to get done. That day we had them printing. By the end of the week, they finished 3 projects that they could not do for months, just because of the additive process that we incorporated. Within Netflix are collaborators like Boeing and Lockheed and others. And we had a project, a three-way project between Netflix, Boeing, and ourselves, where Boeing wanted an IoT device. They designed it. They have their own technology on how to design it. They were the primary people for this project, and they actually had a commercial use for it. Well, imagine a large plane, and imagine what a factory looks like, the manufacturing facility that builds a plane. It's huge. They actually lose forklifts. They lose things across, whether it's a tool or people aren't where they're supposed to be. So they were looking for, so they were designing an IoT device they could put on everything. So they know where everything is. If something's not in the right place, and it could be a safety hazard as well, but something's not in the right place. So they wanted to design this IoT device using additive electronics. So the project consisted of us printing 400 units of their design, 4-layer board on Kapton, as a wearable or so forth. We accomplished it. That was only their proof of concept. Now Boeing has a couple of our printers working on other projects. They kind of bring us along as support for these projects, but these printers are good. So this printer is 12 by 24 inches. So you can print a whole lot of boards at one time. 12 by 24. One operator can run 2 or 3 of these printers. We're working on our next printer, which is going to incorporate aerosol jet, not only inkjet for the fine line prints. We can only get about 50 micron spacing. We're going to want to get down to 10 micron spacing. So we're adding other features as we grow and keep going. Current applications in the space, this is pretty important to us. We are in all of these spaces right now. These machines, these printers, and additive manufacturing of electronics is being used everywhere, from wearables to display screens, sensors, photovoltaics, semiconductor manufacturing, really big right now. We've developed a new method right now that we're just getting patented right now, and is being worked within the CHIPS Act of doing packaging for semiconductors, because we've developed a new dielectric that has a very low coefficient of thermal expansion. So it's ideal. So as we're trying to onshore a lot of semiconductors and semiconductor technology, into the U.S. and take it away from other areas, foreign entities, we're also trying to do it in a different way. So we're doing it additively. We're not doing it in all the traditional ways. I think that's it. Can I answer any questions?
Do any honors?
Yeah, we have a high frequency dielectric. We have different dielectrics. So we have a high frequency dielectric. We are working on one with ITO. So we have a dissipation loss at 10,000 gigahertz of around 0.004. Yeah, so we get we got it there.
As far as power, like the board,
we just stack more silver where we want it.
Fine doing it.
Yeah. So remember, it's 100% silver. Other ways of like screen printing, they have silver particles in there, so they have fillers. So now you have a lot of resistance at it. So
you have like pure silver.
It turns into pure silver. So we have bulk resistivity. Anything? Okay.